viewers, this is 300 Plus Academy, where all we do is exams tutoring, ensuring that you ace your next exam. Still on glass laws, talking chemistry. We'll be looking at Graham's law of diffusion. It was discovered that the heavier a gas is, if a gas is heavy, then the movement of the gas is going to be slow. Take for example, if I have sulfur oxide is 64 gram, and if I have oxygen is 32 gram. If oxygen and sulfur oxide were to diffuse, then it means that sulfur oxide is going to diffuse through whatever partition or from one region to another quite easily than sulfur oxide will. That is because sulfur oxide is a lot heavy. So the implication of this is that the rate of diffusion of a gas is ordinarily inversely proportional to the mass. In this case, the molecular mass. The heavier a gas is, then the slower the rate of diffusion. Looking at Graham's law, this the rate of movement of gas, the rate of diffusion or spread of gas, that is what Graham's law tries to explain. It states that the rate of diffusion of a gas is inversely proportional to the square root of its density or square root of its molar mass, provided that the temperature and pressure remains constant. What this means is that we are saying that when we talk about rate, normally, rate means volume of a gas in cm cube, rate of a gas in cm cube, divided by the time it takes the gas to spread in seconds, so that the rate is actually in cm cube per seconds. That's it. So the rate of diffusion of a gas, is inversely proportional to the square root of its density. What this means is that R equals to K over square root of the density, and the implication of that is R square root of the density is a constant. So in this case, once we have a constant, it means R1 square root of the density of the density of the first gas equals to R2 square root of the density of the second gas. This will then mean R1 over R2. That's if this comes here, then this is moving here, equals to square root of the density of the second gas divided by square root of the density of the first gas. So that when you look at this, this is the second gas here, this is the second gas here, this is the first gas here, this is the first gas here. It goes this way, talking about the rate of diffusion of gas. Similarly, if we are to use the molecular mass, it means the rate of diffusion of gas, we say, is inversely proportional to the square root of the molecular mass. So the implication of this is that R equals K over square root of the molecular mass. So this comes here, R square root of the molecular mass equals to constant. The implication of this is R1 square root of the molecular mass of the first gas equals to K. So, okay, R1 square root of the molecular mass of the first gas equals to R2 square root of the molecular mass of the second gas. So this means R1 over R2 equals to square root of the molecular mass of the second gas. Now, this is going to come here, divided by square root of the molecular mass of the first gas. This is what we are going to have, still 2, 2, 1, 1. And of course, according to your salts, it means you can say R1 over R2, you know, and this can mean square root of the molecular mass of the second gas divided by molecular mass of the first gas, and you won't go wrong. Also worthy to note that since the rate of the first gas here is V1 over T1 divided by rate of the second gas here is going to be V2 over T2 equals to square root of the molecular mass of the second gas divided by molecular mass of the first gas. So let's assume situation whereby volume of the first gas equals the volume of the second gas. The implication of this is that V1 over T1 times T2, this is going to turn upside down, T2 over V2. Since V1 and V2, they are equal, this goes. And then what we have here is molecular mass equals to molecular mass of gas 2 divided by molecular mass of gas 1. So the implication of this is T2 over T1 equals to molecular mass of gas 2 divided by molecular mass of gas 1. So when the volumes are the same, you can see 2, 2, 1, 1. You just use the timing for the rate of diffusion. So this goes this way, not the x, that we have in the case of when the volumes are different. When the volumes are the same, you don't need to even bother to use the volume in the calculation. Just think of the time, and the timing here, we're going to be talking about the molecular mass of the same gas here. So this is what Gram's law entails. So the next thing for us to do is to then move into solving question that has to do with Gram's law. Okay, talking about question 1, it takes a given volume of methane 18 seconds to diffuse through a porous plug. So talking about methane, CH4, the time taken was 18 seconds, okay? To diffuse through a porous plug. How long will it take the same volume? In this case, the volume the same volume of sulfur 4 oxide. So you're basically saying volume of methane is equal to the volume of sulfur 4 oxide here. How long will it take? So you're looking at the time, if we are talking SO2 here, you're looking at the time it will take for SO2. This is the timing for methane. You're looking at the timing it will take for sulfur 4 oxide to diffuse through. So this is quite easy. When volumes are the same, I have said you're going to be saying, okay, the timing, let's say the timing for methane, CH4 now, then you'll be talking about square root of the molecular mass of methane as well, divided by the timing for sulfur 4 oxide, divided by the square root of the molecular mass for sulfur 4 oxide. When the volumes are the same, this is what you're going to have. This is going to be the arrangement. So the timing for methane to diffuse is 18. The timing for sulfur 4 oxide is what we are trying to calculate. What is the molecular mass of methane? That is 16. If you calculate CH4, CH4, C is 12 plus 1 times 4. For 12 plus 4, that's 16, divided by molecular mass of sulfur 4 oxide. If you calculate SO2, SO2 equals to 64. So what you have is 18 divided by timing for SO2 to diffuse. So square root of 16 here is 4, square root of 4 here is 8. Year 1, year 2. So invariably, this will move here. I'm going to have the timing for SO2. 2 will move here. 18 times 2. So the timing it will take for sulfur 4 oxide to diffuse here is 36 seconds. So you can see when the molecular mass was 16, it took 18 seconds. But when the molecular mass increased to 64, it took 36 seconds. So the more the molecular mass, the slower the rate of diffusion of gas. And that ends question 1. Moving on to the second question, it says, if 300 cm cube of hydrogen diffuses through a porous plug. So we're talking about hydrogen here. If 300 cm cube, the volume here is 300 cm cube. If 300 cm cube of hydrogen diffuses through a porous plug in 50 seconds, the timing here is 50 seconds. Okay, how long will it take 100 cm cube of oxygen? You're talking oxygen here. How long will it take? The volume here is 100 cm cube. How long will it take 100 cm cube of oxygen to diffuse through the same plug? How long? The timing it will take oxygen to diffuse is what we're looking at here. So quite direct. When we say the rate of diffusion of hydrogen divided by the rate of diffusion of oxygen, then oxygen should be here. The volumes are not the same, so the molecular mass of oxygen should then be here divided by the molecular square root of the molecular mass of hydrogen. So what that means is we know quite well that rate is volume over time. So when I look at this, the rate here is 300 for hydrogen, that's 300 over 50, divided by what is the rate for oxygen, that is 100 over the timing for oxygen, equals to what is the square root of oxygen? Oxygen is having relative atomic mass of, since it exists as a molecule, this is 16 times 2. It exists as O2, so we have 32 here divided by square root of the molecular mass of hydrogen. This is 2. So what this means, 50 m and 50 is 6. So what this means is 6. This will move up 6 times the timing for oxygen divided by 100. In here, you have square root of 32 divided by square root of 2. You can take this together. This will mean square root 32 over 2. That is square root of 16. Square root of 16. Square root of 16 is going to give you 4. It's going to give you 4. So you're looking at the timing for oxygen to be 4 times 100. Then this 6 will come divide here. So that is 400 divided by 6. And that is 66.67 seconds, and that just answers that question. The timing it will take for that to diffuse is 66.67 seconds. Moving on to the third question. The question says a gas diffused through a porous partition at the rate of 2.3 cm cube per second. A gas diffused through a porous partition at the rate of 2.3 cm cube per second. Okay, let this be the gas. Okay, it diffuses at the rate. The rate here is 2.3 cm cube per second. Okay, under the same condition, hydrogen diffused. Okay, let this be hydrogen. Hydrogen diffused at the rate of 9.2 cm cube per second. Calculate the relative molecular mass of the gas. The relative molecular mass of the gas is the question here. Now, in dealing with this, since the rate looks different, it's better we deal with it this way. If we say rate of hydrogen gas divided by the rate of the gas, then the relative molecular mass of the gas, the square root, will be divided by the relative molecular mass of hydrogen gas. In this case, this will mean 9.2 divided by 2.3 equals to relative molecular mass of the gas is what we're looking for. Divided by the relative molecular mass of hydrogen. And the relative molecular mass of hydrogen, since hydrogen is 1 and it exists as diatomic, so 1 times 2, that's 2, so we put 2 here. And 9.2 divided by 2.3 give us 4. This means 4 into square root of relative molecular mass of gas divided by 2. Squaring both sides, okay, square is going to take out this square here. So this is 16. This is 16 times 2 equals the relative molecular mass of the gas. We try as much as possible to stay away from decimals when we can. So the relative molecular mass of gas here, the relative molecular mass of the gas is 32 gram, and in this case that gas is very likely to be oxygen. So that ends question number 3. So for 30 cm cube of a gas, okay, we have a gas here. Volume is 30 cm cube. 30 cm cube of a gas, the empirical formula of which was CH3. The empirical formula here was CH3, diffused through a porous partition in 45.2 seconds. The timing it took to diffuse is 45.2 seconds. 30 cm cube of hydrogen diffused through in 11.7 seconds. When you talk hydrogen, 30 cm cube of hydrogen, you're talking about the same volume here, so it's going to be inconsequential. 30 cm cube of hydrogen diffused through in 11.7 seconds. The timing here is 11.7 seconds. Under the same condition, what is the molecular formula of the gas? Of course, you recall that molecular formula equals to empirical formula times a certain n here, and for me to get this n, I have to say the molecular mass divided by the mass of the empirical formula mass. Okay, so this I'm going to talk about later, but first we need to get what the molecular mass of the gas is going to be. So I need to first of all know the molecular mass of the gas. What is that going to be? So when I look at this, the volumes are the same. If the volumes are the same, I have said you're going to say T, time taken for the gas to diffuse, divided by the time taken for hydrogen to diffuse. In this case, I'm going to be talking about relative molecular mass of the gas divided by molecular mass of hydrogen. You can see this. So for the gas, this is for the 5.2 divided by 11.7 equals to molecular mass of the gas divided by, for hydrogen is going to be 2. So for the 5.2 divided by 11.7, that is 3.86. 3.86. Of course, this will mean square, because if I square both sides, this is going to mean molecular mass of gas over 2 all squared. This we take out this, so 3.86 square, this is going to give us 14.9 times 2 will come here, times 2 equals to molecular mass of gas. So the molecular mass of gas here equals to 29.8 gram. That's approximately 30 grams. So that is the molecular mass of the gas. So by the time we come here now, N equals to, the molecular mass is 30 gram. 30 gram divided by 30 divided by, empirical formula here is CH3. Carbon here is 12. Hydrogen here is 1 times 3 plus 3. That is 15. So that's divided by 15. I'm going to get 2. Now that my N is 2, my molecular formula is going to be empirical formula times N. So that's CH3 times 2. C times 2, that's C2H6, and that is ethane gas. So that is how it works. This is just linking Graham's law with empirical and molecular formula. And with that, we have come to the end of Graham's law of diffusion. Remember to turn on the notification bell, hit the subscription button, and of course, share with your peers. From myself and the team here, it's bye for now.